We can do something very similar with a graph of acceleration versus time. We have an acceleration. This acceleration doesn't necessarily represent the acceleration that goes with this velocity, but actually it kind of does. And between time t0 and tf, we could subdivide this graph into trapezoids or approximate trapezoids. And what's the area of a typical trapezoid tell you? Well, the area of a typical trapezoid is going to have a base delta t, and you're going to have an acceleration on corresponding to one altitude, acceleration corresponding to the other, and you're going to have an average acceleration in between. To the extent that this line is straight, then the area of this trapezoid, as you should understand by now, is equal to a bar delta t. In other words, the average altitude times the delta t. Remember, we can trim this into a rectangle with dimensions a bar by delta t, so clearly that's going to be the area. That area represents what? Well, a bar is delta v over delta t. Average acceleration, remember, is the rate of change of average rate of change of velocity with respect to clock time, which is change in velocity over change in clock time. So that average acceleration times delta t is going to equal delta v. So the area of any given trapezoid corresponds to or represents the change in velocity for that given time interval. If we add up all the a bar delta t's from all the trapezoids, shrink the delta t's down to where we can't tell any difference at all between the straight line and the graph, and take the limit so there is no difference, then the sum of all our a bar delta t contributions from all these trapezoids is going to be the total change in velocity between t0 and tf. That is, then, the area under this curve is going to be the integral from t0 to tf of the acceleration function with respect to t. That's going to equal the vf minus v0, the total change in velocity on this interval.